An increasing number of developers are switching from object-oriented programming to functional programming as a way to minimize the potential for bugs in their code while maximizing its readability and reusability. Functional programming is an increasingly popular coding paradigm that's been championed by languages like Lisp and Haskell, and its features are natively supported in JavaScript. Writing code using functional programming concepts is the single most important approach you can take to ensure your applications are maintainable and scalable. In this course, I'll show you how to program in the functional paradigm. We'll start off with the basic concepts of functional programming and how it compares to object-oriented programming, and then move on to first-class functions and how to work with them in JavaScript. We'll then move on to seeing how functional programming makes working with data structures very straightforward, followed by some more advanced concepts such as recursion and partial application. Finally, we'll close out with a few interesting challenges that will help you improve your functional knowledge even further. Join me in my course to learn functional programming with JavaScript ES6 to see how you can take your code to a whole new level. To get the most out of this course, there are a few prerequisites that it would be helpful for you to know. The first is a basic knowledge of JavaScript, and ideally some experience with ES6 syntax. If you're not already comfortable with ES6 syntax, it's not hard to learn. If you're interested, I'd recommend checking out one of the ES6 courses in our library. It'd also be helpful for you to have some experience with basic command line operations. All we'll be using for this course is basic commands like mkdir to make directories, cd to change directories, and ls to see the contents of a directory, as well as a few commands specific to Node.js. Keep in mind also that if you're on Windows, the commands might be a little different. There are articles out there like this one that show many of the basic Linux commands and their Windows equivalents. And finally, since I'll be using it as a reference point throughout this course, a basic knowledge of object-oriented programming concepts would be helpful to have as well. And even if you're not familiar with object-oriented programming, it's not a big deal. You should still be able to follow along comfortably with the examples. While I highly recommend that you follow along with me as I write the code, I've also included the finished state for all the code that I write in this course in the exercise files for your reference. So basically, this course is for low, intermediate to professional developers who have a desire to improve their code by learning and applying functional concepts. If you fit that description, then this course is definitely for you. Let's install the tools necessary for this course. Node.js will be really important for running our code, and installing a few libraries we'll be using to make our programming easier. If you're not already familiar with Node.js, all you need to know for this course is that Node.js is an incredibly popular platform that allows you to run JavaScript code outside of the browser. This is really helpful since it means your JavaScript code doesn't have to be loaded and executed as part of a web page. In other words, you can write a single JavaScript file and run it from the command line. If you don't already have Node.js installed, you can download it from Node.js's website, nodejs.org. We're going to click on this button here and download it. And once it downloads, we're going to click on it to open it. And this should take you through the steps required for installation. Note that if you're using Windows or a Unix distribution, the steps might be a little different, but Node.js has instructions for all of these as well. And once you have Node.js installed, you'll want to make sure that you have the most recent version of NPM installed. We'll be using a few libraries in this course, and NPM is a package manager for Node.js that allows us to easily install them. To install the most recent version of NPM, just open your terminal and type npm install-g npm at latest, and you might need to run this with sudo as well. After that, type npm-v, and it should show the latest version. If the npm and Node versions on your computer are higher than mine, don't worry about it, everything should still run correctly. But I do highly recommend having at least these version numbers here. And that's all there is to it. Node.js and npm are now installed on your computer. Before we get into learning functional programming with JavaScript ES6, let's set up an npm directory that we can use to run our ES6 code. Open up a terminal and use cd to navigate to whatever parent directory you want to store the directory for this course in. I'm going to use documents. And then use the make directory command to create a new directory. For example, functional ES6. And then use cd to move into that directory. And once we're inside here, we want to set up our directory as an npm package. And we'll do that by running npm init-y And the Y flag here sets up an npm package with all the default values. If you want to override the default values for your directory, just leave off the -y flag. And now that we've set up our directory with npm, we can install the npm packages necessary to be able to execute ES6 code with Node.js. Currently, Node.js doesn't have native support for ES6 syntax, so we need to use a tool called Babel to act as the middleman between the modern ES6 syntax that we're going to write and common JS syntax which Node.js can run. This might sound complicated, but it isn't. There are just 2 steps we need to take in order to get it working. The first thing we need to do is install the necessary Babel packages. And we do this by simply running npm install --save @babel/core @babel/node and @babel/preset-env. And hit enter. And this will run for a little while. But once it finishes, the second thing we need to do is create a new file in our directory. In order to do that, let's open up our directory in an IDE. I'm going to use VS Code here, but feel free to use whatever editor you're comfortable with. So let's open our directory. Mine is in Documents Functional ES6. And inside this directory, we're going to create a new file, and we're going to call it .babel.rc. I'm going to zoom in a little bit here so that you can see it better. And all we need to do here is create a JSON object with a single property called presets. And the value of this property will just be an array with a single string that says @babel/preset-env. And then we save that file, and that's all we have to do. We shouldn't have to worry about this file ever again for the rest of the course. Now comes the most important part, running our code. From now on, I'm going to be running our code from VS Code's built-in terminal. But you're free to use whatever terminal you want. So normally in Node.js, we can run our code by typing node and then the path to our file and the file name. So for example, source/myfile.js. But since we're going to be writing our code in ES6 syntax, which isn't yet natively supported by Node, the command we're going to use instead is npx babel node and then the path to our file. So let's create a very simple file. We'll call it helloworld.js. And inside it, we'll type some code with very basic ES6 syntax. We'll say const, say hello, and that'll be a function that takes our name and with backticks says hello, name. And after we've typed this out, let's just call our function with our own name. And now to run our code, make sure you're in the right directory and type npx babel-node and then hello world.js. And hit enter, and we should see the result. And that's all there is to it. That's how we'll be running all the code in this course. It's also worth noting that if you want to play around with this code without writing it in a file first, you can also just type npx babel node without a file name and hit enter. And it'll open up this read a value print loop in our terminal where we can test out different statements. Keep in mind also that from now on, when I run code in the course, I'm going to be running it from the exercise files folder. The only difference that makes is that the file paths in my commands might be a little different. So when you're running your own code, just make sure that the file path points to the correct file. So the big question most people ask when they hear about how useful functional programming is what exactly is functional programming? Well, to answer this question, it might be helpful to consider the question of why we would want to use functional programming in the first place. In other words, what are the problems that functional programming sets out to solve? Well, if you currently use an object-oriented programming language such as Java or C++, or especially a procedural programming language such as C, you've probably run into this problem before. There are certain bugs that are difficult to track down and fix, partly because they're hard to recreate, it takes a long, convoluted series of steps to make them show up, and partly because even when you figure out how to recreate them, it's next to impossible for you to keep track of all the changes that occur while the program is running. In a typical enterprise-sized program, thousands of variables are being operated on in thousands of different places at runtime, and the application can get itself into buggy states which can be difficult to recreate. This is exactly the type of situation that functional programming aims to avoid. Once you learn to think and program in a functional style, this type of situation will become much less frequent. You'll learn many techniques that can be used to create very large, powerful, and virtually bug-free code bases that are composed of many smaller, self-contained, and easily testable parts. So then, at its core, functional programming is concerned with taking the large number of complex ideas present in any large computer program and organizing them in a coherent way, while at the same time making sure that the code remains easy to test and modify. Of course, this sort of organization is what object-oriented programming aims to do as well, although it achieves it with only varied success. The difference between object-oriented and functional programming is in the choices they make with regards to organizing code. As you probably know already, the basic idea behind object-oriented programming is that humans think in terms of objects and relationships between these objects, and therefore computer programs should be organized in terms of objects so that we can leverage our existing thought patterns to write programs more easily. The problem with this, of course, is that our thought patterns are often not as well defined as we sometimes like to think. Once we go beyond contrived examples such as SUV is a subclass of car, car is a subclass of vehicle, which demonstrates the concept but isn't very helpful, the object-oriented programming doctrine doesn't provide much guidance regarding code organization. We're left with a rather daunting array of concepts like interfaces, subclasses, constructors, public, private, and protected data, accessors, mutators, and method overriding, all of which form a complicated web of relationships and are prone to abuse by all but the most experienced and disciplined programmers. On the other hand, functional programming aims to bring the precision of mathematical functions into computer programs. While there will always be room for human error in programming, no matter what paradigm is being used, adding the provable certainty that comes with mathematics into computer programming makes it far easier to avoid bugs. Imagine if we were able to represent all parts of a computer program as simply as a mathematical function such as function of x equals x plus 1. Where could a bug possibly be hiding in functions like this? We'll look further into the details of functional programming along with the many differences between it and object-oriented programming throughout the rest of the course. Since many of you are probably most familiar with object-oriented programming, I'll continue to use it in a lot of comparisons with functional programming to clarify the concepts I show you. One of the first things you'll want to understand about functional programming is that it's a declarative style of programming, as opposed to things like object-oriented programming and procedural programming, which are imperative styles of programming. What this means is that functional programming puts more focus on what things are as opposed to how to get them. A simple example of this would be if we were to talk about houses. If we wanted to describe a house in a declarative way, if we wanted to describe what a house is, we might say that a house is a foundation, 4 walls, and a roof on top. On the other hand, if we were describing a house in an imperative way, if we wanted to describe how to make a house, we might say, in order to make a house, you need to pour the foundation, build 4 walls, and then put a roof on top. Let's expand on this a bit and look at a more programming-related example. Let's say that we want to write a program that tells us the average of an array of numbers. Imperative programming would specify the steps required to calculate the result. Something like this. First, we set x equal to 0. Second, we add the first number in the array to x. And then, we repeat step 2 for the rest of the numbers in the array. And finally, we divide x by the length of the array. Now, unless you've worked with functional programming before, this is probably how you're used to writing programs, thinking of how to get the result. On the other hand, if we wanted to solve the same problem in a declarative way, we could simply say that x is the sum of all the numbers in the array divided by the length of the array. Or if you're more mathematically inclined, we could rewrite it using mathematical notation like this. Now, if it never occurred to you that it's possible to write programs in this way, by simply stating what something is, you're not alone. You probably notice that talking about things declaratively, talking about what they are instead of how to get them, feels a lot more natural, and well, frankly, it's a lot easier for many problems. This way of talking about things may also remind some of you of mathematical functions such as these. And as I mentioned before, This is one of the main ideas behind functional programming, to bring the precision of mathematical functions into our programs. As you may have figured, this is also where functional programming gets its name. So it's all very easy to say that functional programming brings the precision of mathematics into programming, but what does that mean exactly? Well, there are three main concepts behind functional programming which allow us to do just that. These concepts are 1. Immutability, 2. Separating functions and data, and 3. First-class functions. Over the course of the next few videos, I'll go into depth on what each of these concepts means, contrast it with how other paradigms do things, and explain its advantages. The first major concept of functional programming is immutability, and it's a concept that may surprise a lot of people at first. Most programmers learned early on that you could assign a value to a variable. For example, we can define a variable called x and store the value 5 in it, and then later on in the program, we can change the value of that variable to some completely different number, and later on we can change its value again, and so on. However, in functional programming, this is not allowed. When we say that x is equal to 5, we mean that for the rest of the program, x will only ever be 5. There's no way we can change it. In short, immutability means that most of the values in a program are constant, which in JavaScript means using the const keyword instead of the var or let keywords. Another way to think about it is this. In object-oriented and procedural programming, we treat variables as buckets that we can put values into. We call this assigning values to variables. So at one point in time, x might hold the value 3, at another point it might hold the value 10, at another point it might be -4, and so on. On the other hand, in functional programming, we don't assign, we define. Instead of naming buckets that hold different values at different times, we name the values themselves. When we say that x equals 3, we don't mean that x is a container that's currently holding the value 3. We literally mean that x is 3. In the same way that pi is 3.14159, etc. Could you imagine changing the value of pi? Of course not. Functional programming treats all values as if they were as concrete and unchanging as pi or any other mathematical constant. And so, once we've defined x, for the whole entire program, x can never be anything else. It's just another name for whatever value we've defined it as. At first glance, this may seem strange to most programmers. After all, what good is a program where you can't change anything? How can a program like that be useful at all? Let's look at a quick example. What if, in a certain theoretical program, we have an employee and we want to raise their salary? Well, in object-oriented programming, of course, we can just change it directly, usually by calling a member function like this. In functional programming, on the other hand, we would instead define a new constant that represents the updated data and then use this constant in our future calculations. Notice here also that I'm not using the new keyword as we do in object-oriented programming. I'm just defining our data in a JavaScript object. We'll learn more about why this is later on. The advantage of immutability, and the reason that functional programming places such an emphasis on it, is that it frees us from having to deal with state change. When a program contains many variables that are all changing constantly at different times, it can be very hard to know what state a program is in at any given point in time. As programs increase in size to include thousands or even millions of individual variables, this can lead to extremely hard to find bugs and an overall fragile codebase that programmers are afraid to make changes to. This is a problem that even test-driven development can't solve completely, since the task of testing all possible states that a program might get itself into is nearly impossible in programs of considerable size. In functional programming, on the other hand, we start off with an immutable set of data as a single source of truth, and then we use functions to combine this data piece by piece and transform it into useful information. This data is usually retrieved from a database or some other memory storage. There are two powerful advantages to this approach. The first is that the original data in a program will always remain intact, which makes bugs much easier to find. The second is that programs constructed in this way are much easier to keep track of, since you can focus on any given piece individually. The only thing that determines the output of a given piece is the input. We don't have to think about the entire system all the time. If the concept of immutability doesn't quite make sense to you yet, or if the advantages don't seem apparent, don't worry. Later on in the course, we'll take a look at many examples that incorporate immutability. For now, just remember that in functional programming, all data is immutable, so use const instead of let or var. The second main concept of functional programming is the separation of data in functions. This is a case where functional programming is directly in contrast with object-oriented programming, where data in functions are almost always grouped together. Let's see what this looks like. First of all, for our purposes, let's discuss what data in functions actually are. For our purposes, data might be any values that a program contains: people's names, addresses, and social security numbers in a payroll program, the models, years, and colors of cars on a used car website, the positions, health levels, and weapons of characters in a video game, anything. All of this is data. In object-oriented programming, this data is usually wrapped up inside objects as member variables, and the only way we can access it is using an object's methods. In functional programming, on the other hand, this data is represented by simple arrays and hashes, or in this case, JavaScript objects. And a function is any operation that we can apply to our data to convert it into useful information. For example, if we want to find the average salary of programmers at our company, find all the cars on our website that were made after a certain year, or find if two characters are colliding in our video game. In object-oriented programming, functions are wrapped up inside objects along with the data that they operate on, and allow us to access or make changes to that data. In functional programming, on the other hand, functions are completely separate entities from the data that they operate on. In order to operate on given data, the data must be passed as arguments to the function instead of using the this keyword as in object-oriented programming. And because of the rule of immutability, they should never make changes to any of the data they touch. They only return a modified copy of that data. If you're coming from an object-oriented background, it may seem strange to you that functional programming places an emphasis on keeping data in functions separate, since one of the central concepts of object-oriented programming is that we put data and the functions related to that data together in objects. To understand why it makes sense to keep data and functions separate in functional programming, it might be helpful to think about why we keep them together in object-oriented programming in the first place. The main reason that it's useful to keep data and functions together in the same object is that this allows us to interact with the member variables of an object without touching them directly. What's wrong with touching variables directly? Well, if we give programmers direct access to variables, they can, and in my experience will, change them in ways that they're not supposed to. Consider the simple case of a person object with publicly accessible properties first name, last name, and initials. Now, if we allow programmers to change these properties directly, they have to remember to reset initials every time they change either first name or last name, which they're almost certain to forget somewhere, which introduces bugs in the program. The most popular solution to this is to make the variables private, which in JavaScript is usually done by just adding an underscore before the variable name and telling developers not to touch it. And then we allow programmers access to the variables only through functions, which makes sure that the variables are kept up to date. In functional programming, however, we don't need to worry about making all our data private because programmers can't alter the data in unwanted ways. Because of the rule of immutability, which we discussed in the previous video, the data remains a constant source of truth. Note that in JavaScript, we need a little extra help to keep developers from modifying our object properties, but we'll talk about that in a coming video. If we want to transform the data in some way, such as changing someone's name, we simply define a new constant that represents the updated data. We then use this updated constant in all our future calculations, knowing exactly what data it represents. Let's take a look at a simple example to demonstrate how functional programming and object-oriented programming handle functions and data differently. Let's imagine the classic example of creating a simple to-do list program that helps people keep track of tasks they need to complete. Let's look at what an object-oriented approach to this program would look like. First, we'd create a to-do item class that contains properties such as the name, category, and deadline for the item and whether or not it's been completed, as well as functions such as change name or mark as done. And then, of course, our getters to access our private variables. Then we might have another class called to-do list, which contains an array of to-do items, as well as functions for adding or removing items or sorting them in different ways. In functional programming, on the other hand, we'd keep the data and functions separate. Remember that in functional programming, instead of wrapping up our data's properties as member variables inside classes, we usually represent data using constructs such as arrays or hashes, which in JavaScript somewhat confusingly we call objects. So for this program, we might have JavaScript objects that represent to-do items, with name, category, and deadline properties, and the list itself, which we would simply represent with an array that holds a bunch of to-do items. Then, outside of these classes, we define the functions for combining or transforming our data, such as sorting it or marking an item as done. The third major concept of functional programming is something called first-class functions. This is where things really start to get interesting and where the power and flexibility of functional programming really starts to shine through. So, what exactly do we mean when we talk about first-class functions? Well, in object-oriented programming, we generally treat data and functions as different types of entities. We would probably never think of, for example, creating an array of functions or passing functions as arguments to other functions, or even stranger, returning functions from other functions. However, in functional programming, it's not only possible to do these things, it's in fact a source of tremendous flexibility. This is exactly what we mean when we say that a language supports first-class functions. It allows us to treat functions in a very similar way to how we normally treat other values such as numbers, strings, and objects. But hold on a minute. Doesn't this go against what I said in the previous video about the separation of data and functions in functional programming? Well, at first glance it might seem like it, so let me clarify. In object-oriented programming, since functions and data are both defined within the same class, they tend to be tightly coupled. In other words, the functions inside a given class usually reference the data that they operate on directly, as is the case here with this.name. In other words, you generally can't take a given function and remove it from the class it's in and still have it work on its own. In functional programming, on the other hand, we design our functions specifically so that they work in isolation. All of the data that a function needs to operate on is passed in through the arguments, and the only thing that will change the output of the function is a change in the arguments. In other words, functions aren't influenced by any kind of internal or external state. There's a name for this kind of function. We call them pure functions, and in functional programming we try our best to make every single one of our functions pure. And this is what we mean when we say that we want to keep data and functions separate. Now, you might be wondering why we'd want to do stuff like this. What could we possibly gain from doing weird things like having arrays of functions or passing functions as arguments? In fact, this simple change in mindset toward functions opens up a world of possibilities in terms of software design. It gives us a lot of flexibility and greatly increases our opportunities for code reuse. It also allows us to do useful things like combine existing functions to create new functions. We'll see in the next chapter how this is done and what its implications are for our programs. So I talked in a previous video about the importance of immutability in functional programming. Immutability allows us to avoid the many bugs that occur in computer programs as a side effect of state change. It also means that we don't have to worry about using private variables to avoid changes coming from unexpected places, since we simply can't make changes to any piece of data. That being said, if we want to ensure complete immutability in JavaScript, there's something we need to keep in mind. While using the const keyword prevents us from directly changing the value of a piece of data, for example, if we say const x equals 5, we can't simply say x equals 6, since this will throw an error. However, using const in JavaScript is a little funny when working with arrays and objects. For example, if we define an array called numbers, like this, const numbers, 1, 2, 3, 4, 5. We can never directly redefine numbers as a different array like this, numbers equals hello. But we can modify the individual elements of an array like this, numbers 0 equals 100. And JavaScript won't complain about this at all, even though we've defined our numbers array using the const keyword. Also, if we're not careful, we can accidentally call a mutating array method such as reverse on a supposedly immutable array, like this, numbers.reverse. And this will actually modify the original array without any complaint from JavaScript. And the same is true for objects as well. If we define an object called person, const person, with name and age properties, name John Doe, age 34. We can never directly redefine person as another object like this, person equals name Bob. But if we try and reset a property of our object like this, person.name equals Bob, JavaScript won't complain, even though this is modifying our data. Now, I'm going to show you an approach that we can use to prevent mutation in our code, and this is by using ESLint rules. If you've never worked with or heard of ESLint before, it's an extremely helpful tool that helps you catch errors or stylistic flaws in your code. ESLint won't add anything extra to your code. We can simply run it and it looks at our existing code and tells us any problems it finds, for example, if we're doing accidental mutation. Now, there are many different ESLint plugins that we can use depending on our coding style and concerns. There are ones that check for correct indentation, ones that make sure you put semicolons at the end of every line, etc. But for the purposes of this course, the lint rules we're interested in are the ones that will automatically tell us if we try and mutate anything in our code. There are several existing plugins that already implement this functionality, and the one we're going to use is called ESLint Plugin Immutable. I'm not going to go through all the details about ESLint here, but I'll just walk you through the steps required to get this set up. The first thing we're going to do is open up a terminal inside our exercise files folder. I'm going to use the integrated terminal inside VS Code, but you're more than welcome to use Mac's built-in terminal as well. And then inside our exercise files folder, we're going to initialize an npm package with npm init-y. Once we've done that, we'll install ESLint as a dev dependency by typing npm install --save dev ESLint. Then we'll initialize ESLint for our project by running npx ESLint --init. And then it's going to ask us a series of questions, so we'll answer those. And to make things easier on ourselves, we're going to select Use a Popular Style Guide when it asks how would you like to define a style for your project. This enables us to use a predefined set of rules. And we're going to select Airbnbs. And now we see that ESLint created this ESLintRC.js file for us. This file tells ESLint what to look for in our code. The next thing we're going to do is install the ESLint plugin immutable package for our project. So in the terminal we'll type npm install --save dev ESLint plugin -immutable and hit enter. And then all we have to do is add some of these rules to our ESLintRC file. So we'll open up ESLintRC.js and add a plugins property right above rules. Plugins. And it's going to be an array. And then we simply add our immutable package to it, like this, immutable. And don't forget to add the commas. Then inside the rules object, we're going to add a rule from immutable. Specifically, we're going to use the immutable/no-mutation rule. And we're going to give it the value 2 because we want ESLint to treat this as an error if it finds it, not just a warning, which would be 1. And for those of you who are wondering, if we want to specifically disable a rule, we could set this value to 0 like this. But we're going to leave it as 2. Let's save our file as well. So now, if we delete all this code and rewrite some code that we might find when we're accidentally mutating our data, like this, const person equals name, John Doe, and age equals 34. And then we try and mutate the name property, person.name equals Bob, and then we save our code. And then if we go into our terminal and type npx ESLint, and then the directory that we want to run lint on, in this case, just the current directory we're in, so we'll use dot, and hit enter. We see that in addition to a few other lint errors, ESLint also gives us an error saying that no object mutation is allowed. Keep in mind also that if you don't want to use the default rules from Airbnb, you can go into your ESLintRC and simply delete extends Airbnb base from the object. But I'm going to leave it in there. So there you have it. When we're creating a functional code base and want to ensure that we don't accidentally mutate any of our data, we can set up ESLint to catch any mutations for us. Since throughout the rest of the course we want to take full advantage of many of ES6's features, the first thing we're going to do is really solidify our experience with the alternative syntax that ES6 provides for defining functions. In JavaScript prior to ES6, the most common way of defining functions was to use the function keyword. And there were two ways of doing this, either by writing function, the function's name, and then the arguments like this, function, my function, then the arguments arg1, arg2, etc., and then brackets, followed by the function body, or by using var, let, or const to define our function like this, const my other function equals function, and then the arguments arg1, arg2, and then brackets followed by the function body. Now ES6 allows us to get rid of the function keyword completely by providing us with a new syntax called arrow functions. Many of you may already be familiar with arrow functions, or you may not, but either way, since I'll be using this syntax heavily throughout the rest of the course, let's go through some examples to get comfortable with them. Let's start with a very simple example, a function that takes two number arguments and adds them together. The most long-winded way to write this using arrow notation would be like this. Const add, we'll call our function add, equals the arguments, x and y, and then the arrow, and then brackets, and then we're going to say const sum equals x plus y, and finally we're going to return the sum. Now, as I mentioned, this is a rather long way of writing this function using arrow syntax, but it'll give us the chance to see a few nice things that arrow functions let us do syntax-wise for specific cases. For example, if we cut out this intermediary sum constant, we can simply return x plus y like this. Delete that, and return x plus y. And this is where arrow functions can start looking really nice, because when the only statement in a function is its return statement, we can drop both the brackets, delete those, and we can also delete the return keyword, like this. Personally, I find this nice compact syntax to be much more beautiful than using the function keyword with the brackets and the return keyword. Once we get into more complex functional concepts, the arrow function will contribute a lot toward keeping our code concise and uncluttered. If at any point you find yourself getting confused by this syntax, just remember that it's a shorthand for the regular function syntax. There's one more nice thing that the arrow function notation lets us do syntax-wise. Let's say that we have a function with only one argument. In this example, we'll make a function that takes a single number and doubles it, like this. Const, we'll call it double, equals number, which is our argument, and then it returns number times 2. Now, when we define a function like this with only one argument, arrow syntax allows us to completely drop the parentheses around the argument, like this. Again, don't let this syntax confuse you. At its core, it's just a shorthand version of writing this using the original non-ES6 syntax, like this. Const double equals function number, brackets, and then return number times 2. And what does it look like when we have a function with 0 arguments? Well, we can't just have a blank space with no arguments in it. So when we define a function with no arguments, we just put 2 empty parentheses like this. Const say hello equals parentheses console.log hello. One more thing to keep in mind is that if we want to write an arrow function that returns an object, and we're omitting the brackets, we need to wrap the function body in parentheses like this. Let's create a function called getPersonData. So const getPersonData equals empty parentheses. And then since we're returning an object, we have to put parentheses and then brackets. And then we can define our object properties. So we'll say name, John Doe again, age, 34, job, programmer. Note that here, if we didn't wrap the object we're returning in parentheses, like this, it would look to the interpreter like we wanted to use the brackets to define the body of our function, and that's why we have to wrap it in parentheses in this specific case. So then, let's just review the different ways we can write the parts of an arrow function. Let's say const my arrow function And if our function has 0 arguments, then it's just empty parentheses. And if we have 1 argument, we can write it without the parentheses, like this. And if it's 2 or more arguments, we're still required to wrap the arguments in parentheses, like this. And when we're writing the function body, if our function contains more than just the return statement, we have to wrap it in brackets like this. And we also have to use the return keyword. Otherwise, if our function body only has 1 statement, we can simply drop the brackets, and ES6 will automatically return whatever the result of that line is. And we drop the return keyword as well. And finally, if you're returning an object in this case, remember to wrap it in parentheses, like this. I mentioned in a previous video that functional programming treats functions as first-class citizens, meaning that we can treat functions in a very similar way to other types, such as strings, numbers, or objects. In this video, we're going to take a look at what this means for our code, and a few useful things that we can do with it. Let's start off with a simple example. We'll create a function, we'll call it sayHello, const sayHello, and all this function will do is print the word hello to the console. Equals parentheses, arrow, console.log, hello. What we can do now is define another function, we'll call it sayHello2, and set it equal to our function sayHello. Const sayHello2 equals sayHello. We can then call our sayHello2 function in the same way that we can call sayHello, just by adding parentheses to the end, like this. This is true also when we add arguments to our function. For example, if we add a name argument to our sayHello function like this. And in this case, since we only have 1 argument, we can remove the parentheses. And then we'll say plus name in here. We can then add this argument to sayHello2, and it'll be just like if we called it from the original sayHello function. You may have noticed that when we define functions with the ES6 arrow syntax, we use the const keyword. This is exactly the same syntax that we use when defining other types, such as numbers, strings, or objects. And just like with these other types, we can do interesting things when assigning. For example, we can use a ternary operator to dynamically change a function's definition, like this. We can say const myFunction equals, and then some condition. We'll just use true here. And then we can do our ternary operator. And if the condition is true, we can set it equal to one type of function. And if it's not, we can set it equal to another type of function. Now, one possible application of this is for mocking out pieces of our code during development. If we have a piece of code that's especially time-intensive, such as network or database operations, or especially destructive, such as deleting an entire database, it can really get in the way of our development. So what we can do is define a mocked-out version of our function that returns some fake data without doing all the time-intensive operations that the real version of the function does. Let's see what this looks like. First, let's define a constant that tells our application when it's running what sort of environment it's in. We'll call this development. And then we can set it equal to either true or false. Right now, we'll just set it equal to true. And then we'll create a function called fetchDataReal, const fetchDataReal, and then it will just have no arguments for now. And this is where the time-intensive operations would take place. For now, we'll just have a comment there. We can then define another function called fetchDataFake, const fetchDataFake. And what this function will do is simply mock out the data that we expect to get back from our server. For example, if we're expecting to get a person object back, like this. And finally, we'll define the function that would be used elsewhere in the app. This is where we use a ternary operator to decide which of the function definitions, the real one or the fake one, will be used at runtime. We'll simply call this function fetchData, const fetchData, and we're going to use a ternary operator which depends on development. And if development is true, we want to use our fetchDataFake function. And if development is false, in other words, if our application is running in production mode, we want to use the real fetchData. So fetchDataReal. And that's all there is to it. Now, obviously in a real application, we probably use stuff like promises or async await, but for illustration purposes, this example serves its purpose. There are many other applications for this sort of function assignment. For example, if you want to do stuff like A/B testing different implementations of a function for performance reasons, but I'll leave that to you to experiment with. In this video, we're going to look at another example of an interesting thing that can be done with first-class functions. Just as we can create an array of numbers, an array of strings, or an array of objects, because functions in JavaScript are first class, we can also create an array of functions. And why would we want to do something like that exactly? Well, let's say that we have a few different functions that we've created with our nice ES6 arrow syntax, all of which take a single argument and make some sort of change to that argument, like doubling it, or subtracting from it, or tripling it, or adding 5 to it. Now, let's say we wanted to get the result of applying all of these functions to some number. The mechanical way of doing this would be to say something like const myNumber equals 42, and then we would apply our functions one by one to this number. So const doubled equals double myNumber. Const minus 1 equals subtract 1, called on doubled, the result of our last operation, and so on. But what if we have hundreds or even thousands of these functions? Well, what we can do is define an array with all of these functions in it like this. We'll say const functions array equals, and then we'll put each of these functions in this array. Double, subtract 1, triple, and add 5. The first thing to notice is that when we put our functions into the array, we don't put parentheses after them, as you might be used to seeing. This is something you'll get used to while mastering functional programming. The thing to remember is that when we put parentheses after a function, we're referring to the result of calling the function, instead of the function itself. When we want to refer to the function itself, as in this array, we simply use the function's name without any parentheses or arguments after it. So we now have an array of functions that we just want to apply one after the other to some number. The solution now is pretty simple. We just loop through the functions and apply each one to our number. Now keep in mind that the code we're going to write for this isn't the most functional code since it involves mutation, but in an effort not to give you too much too soon, we're going to use a bit of procedural code to prove a point. Later on in the course, you'll learn a more functional version of this code, but for now, it's good enough. So first, what we'll do is assign the number we want to work with to a variable. So we'll say var number equals 42. And now that we have the number that we want to start off with, we're going to use for each to loop over each function in our array and apply it to our variable number. So functions array dot for each. And then this argument will represent each of our functions, and we'll say number equals the function called on number. So after this line runs, our number variable should hold our result. Let's print that result using console.log and then run the program. Console.log number. And then we'll run our program by typing npx babel-node and then the path to our file, which in this case ch02/02_03/start/examples.js. And there we see our result. If you want, you can mess around with the order of these functions and see how that changes things. You can also define your own functions and add them to the array. Another interesting thing that you can play around with as well, that might shed some light on the nature of first-class functions, is to put JavaScript's built-in math functions into our function array. Let's see what happens if we add the square root function, math.sqrt, to our functions array. Remember to pass it without the parentheses since we want to pass the function itself and not the result of the function. Let's save our code, and then run it again to see what happens. And we see that we have our result again. The point here is that we're not just limited to functions that we define. Any function that's defined anywhere can be used in this way, whether it's a built-in function, a function from another library, or one of your own functions. Now that we've seen a few ways that we can treat functions in the same way as other types, such as numbers, strings, and objects, the next step is to look at how we can pass functions as arguments to other functions. Up until now, you've probably been used to passing arguments into functions with the purpose of specifying what the data is that we're operating on. If we pass two numbers into a function called add or subtract, for example, we're specifying the two numbers that we want to add or subtract. But what if, instead of passing arguments into our function to specify what the data is, we could pass in arguments to specify what was done to our data? This is one of the important things that first-class functions let us do. To illustrate this point, let's take a look at two very simple functions, add and subtract, defined, of course, using arrow function syntax. Each of these functions takes two arguments and then either adds or subtracts the two numbers. For example, if we call add with 2 and 3, it'll give us 5. And if we call subtract with two numbers, say 9 and 3, it'll give us 6. But what if we had another function where, instead of passing in the two numbers into this function, the numbers were fixed to say 2 and 3, so we'll create this function called combine 2 and 3, and then we pass in a function that specifies how those numbers should be combined. For example, should they be added, subtracted, multiplied, averaged, etc. So we'll have our function argument here. And then inside our combine 2 and 3 function, we call the function argument on two fixed numbers, we'll say 2 and 3, and then return the result, which is done automatically since this is an arrow function. Now what we can do is take our add or subtract functions and pass them into our combine 2 and 3 function, like this. Combine 2 and 3, add, or subtract. Now when we pass the add function, we end up with 2 plus 3, which of course is 5. And when we pass the subtract function, we end up with 2 minus 3, which is -1. And of course, we can pass in pretty much any other function that we want that combines two numbers and returns a number, and pass that into our function as well. For example, we can pass in JavaScript's built-in math.min or math.max functions, like this. Combine 2 and 3, math.max, and this would give us the maximum of 2 or 3, which would be 3. Now, so far we've been defining our functions separately before passing them as arguments. While for the sake of readability this is often considered a good practice, we can also pass in anonymous functions, which are basically just unnamed functions that we define on the spot as we need them. Using this existing code as an example, instead of creating a new named function for each type of combination, we could simply define it in place. So for example, instead of explicitly defining and passing add, we could just say combine 2 and 3, and then pass an anonymous function, which takes two numbers, x and y, and adds them together, like that. A lot of times anonymous functions can be more convenient to write, since there can be some special cases where our desired functionality is very specific and it's not really worth creating a named function for it. So far we've seen that it's possible to define functions in pretty much the same way we define other things, such as strings or numbers, and we've also seen that it's possible to pass functions as arguments, again, similar to other types. So the next logical thing for us to look at with respect to first-class functions is our ability to return functions from other functions. Now, the usefulness of first-class functions has been kind of limited up until now without this final piece of our first-class functions puzzle. This is the place where the flexibility that first-class functions give us really starts to shine through. So first, let's try to wrap our heads around the concept of functions that return functions. In programming, it's common to hear functions referred to as a black box. You put data into the box and you get some different data out. If we're talking about a function called double, for example, we put one number into the box, say 5, and we get another number out, in this case 10. Or if we're talking about a function called uppercase, we put a string into the box, say hello, all in lowercase, and we get the same string out of the box in uppercase. Now, since JavaScript treats functions the same as strings and numbers, it's possible in JavaScript to have a black box that returns another black box. This other black box then behaves the same way as a regular function. We put data in and get some different data out. This is exactly what we're doing when we return functions. So when we have a function that returns another function, it might help to think of it as a function creator or a function factory. Let's look at the syntax for defining a function that returns another function. This is the part that unnerves the people the most the first time they look at it, but bear with me, once you understand it, it'll be easy. So let's do the simplest possible example. Let's define a function that returns a function that prints something to the console. Const. And I mentioned that it's often helpful to think of these kind of functions as function creators, so let's call this one createPrinter. Now, as with most of our other examples, we're going to define this function using arrow syntax. This function doesn't take any arguments, so we'll put empty parentheses, and it returns another function, which we'll also define using arrow syntax, that doesn't take any arguments, and prints hello to the console. Console.log, hello. The part that confuses people the most about this sort of definition is the double parentheses and arrows. It might take a little practice to get used to reading functions like this, but what you have to remember is that this arrow function syntax is just a shorthand way of writing the much longer version, which would look like this. Adding in the function keywords, and putting in the brackets, and we would want to say return function, and then put this console.log inside of brackets as well. You might find that as you're learning functional programming, it helps you to write your functions like this first, and then reduce them down to the arrow function notation. Pretty soon you'll get the hang of it and be writing functions like this with minimal effort. Now that we have a slightly better idea of how this whole returning functions thing works, let's look at a more useful example. First, let's say that we have a program with 3 functions. Double, const double, which simply takes a number and doubles it. Const triple, which takes a number and triples it. And quadruple, which takes a number and quadruples it. Now, the first thing that you'll notice about these functions is that our code has quite a bit of repetition in it. And this is usually a sign that our code could use some refactoring to increase code reuse. So what if, instead of having to define several different functions with only slightly different definitions, we could have a function that created these variations for us? Well, this sounds like a job for first-class functions. What we're picturing here is a function that takes a number as an argument, and we'll call this function createMultiplier. And it takes a number as an argument, we'll call it y, and then returns a function that also takes a number as an argument, and multiplies its own argument by whatever number we originally passed into the outer function, so x times y. And now that we have our createMultiplier function, we can use it to replace our existing implementations of our double, triple, and quadruple functions, and that will look like this. Let's move these down here, and we can replace double with createMultiplier with the value 2, and we can replace triple with createMultiplier with the argument 3, and finally we can replace quadruple with createMultiplier and passing 4. And we can then call these functions, and it will return exactly the same thing as our original function definitions, except now we're doing it in a more functional, reusable way. Now, the functions that we replaced here were very small and simple, but the same technique can also be used to replace repeated code even when dealing with larger functions that use much more complex logic. We'll see some examples of this later on in the course. In a previous video, we talked about how in JavaScript, it's possible to return functions from other functions, and saw some possible applications of doing this in our codebase. Returning functions from other functions leads us to another very important concept in JavaScript, and this is something called closure. So what is closure exactly? Well, basically closure means that when we define a function that returns another function, the function that we return still has access to the internal scope of the function that returned it. In this case, the function that we return still has access to the constant x, even after we return it. To see what I mean a little better, let's code out an example that demonstrates closure. First, let's create a function called createPrinter, const createPrinter, and this function won't take any arguments. And for illustrative purposes, let's make a function body with more than one line using the brackets. So inside this function body, let's define a constant called myFavoriteNumber and set it equal to whatever you want. I'm going to use 42. Now we're going to return a function that also doesn't take any arguments and prints this number to the console. So we'll say console.log, and I'm going to use backticks here instead of the normal single quotes. We'll say myFavoriteNumber is $brackets myFavoriteNumber, the constant. And then we'll use this by saying const printer equals create printer, and then calling printer. And now if we run our code by typing npx babel-node, and then the path to our file, in this case ch02/02_06/start/examples.js, we see that it prints it to the console. Now, at first glance, this might not seem like anything special, but let's look closer. When we return our printer function by calling createPrinter and then call the printer function, we can see that we somehow still have access to the constant myFavoriteNumber that we defined inside the createPrinter function, even though if we were to try and use this constant directly by typing console.log myFavoriteNumber, we would get an error saying that myFavoriteNumber isn't defined. And this is exactly what Closure is. When we return a function, it still has access to the scope that it was returned from. This is a very important concept, since if it didn't exist, returning functions would be pretty useless in most cases. For example, if it didn't exist, when we called printer here, it would just log out myFavoriteNumber is null or undefined. Now, in order to illustrate Closure further, let's look at an interesting example. I'm going to show you how to use Closure to implement real private variables in JavaScript. This may seem a little ironic in a course devoted to functional programming, since functional programming makes every effort to avoid using these private variables, since they usually mean our code is stateful. But I think this is an excellent example of Closure in JavaScript and will help you wrap your head around first-class functions a little better. So the most common way that I see programmers implementing private variables in JavaScript is by simply adding an underscore at the beginning of the variable name. For example, underscore name. This is supposed to signify to themselves and to other developers that you should never directly use this variable outside the class. However, in my experience, programmers will always ignore this when it's convenient for them. So let's look at a better way. Let's imagine that we want to create a person class. Now, instead of using the class keyword, as many people are used to doing, we're just going to define it as a function that returns a new person object. And that'll look like this. We'll say const person equals function. And then instead of passing multiple arguments to specify name, age, and job for this person, we're going to use object destructuring. And we're going to have name, age, and job properties. And then we're going to define the function body here. And at some point inside this function, we're going to return an object. We'll get to that in a second. Now let's define our quote-unquote member variables. Note that since we've used the variables name, age, and job up in the arguments, we'll have to rename these a bit. What we're going to do is say var underscore name equals name, var underscore age equals age, var underscore job equals job. Now comes the fun part. We're going to use Closure to make these variables accessible to the outside world only through getters and setters. Let's start by writing the getter function for the person's name. We're going to define it as a property inside the object we're returning. We'll call this function getName and define it using the arrow syntax as usual. And finally, inside this function, we're simply going to return the name variable that we have access to. Let's stop and take a look at how we can use this function that we've created so far. First, we'll create a new person object like this. Const me equals person, and then we'll say name, Sean, age, 25, and job, developer. And then, if we want to see the value of this person's name, we can type me.getName. Let's print this to the console to see the result. Console.log. And then let's run our code by typing npx babel-node, and then the path to our file, ch02/02_07/start/examples.js. And we see that it correctly prints the person's name. Now here's the really important part to understand. This getName function is the only way we can access the name variable. If we try to do something like me._name, this will return undefined. And this might seem strange at first, but let's take a look. The object we're returning here doesn't have any name property. The only thing it has is a getName function that has access to the name variable through closure. Let's write the getters for the other two properties now. Here's what that will look like. getAge, we're going to have a function that returns our age variable. And getJob, we're going to have a function that simply returns our job variable. And we can then use these in the exact same way that we used getName. Now let's write the setters for our private variables. Just for the sake of illustration, we're going to leave the name variable without a getter, signifying that it's a property of a person that can't be changed. Let's see what the setter for our job variable will look like. We're going to add it to the same object that we're returning, along with all of the getters. We'll call this function setJob. This function will take one argument, which is a string signifying what we want to change the job variable to. We'll call it newJob. And then inside the function, we're just going to set our interior job variable equal to the argument that we pass in. _job equals newJob. Now let's see what using this new function will look like. If we go back to this person object that we defined earlier, we can call getJob and see that we have access to the job variable through closure by running our code again. We can then call our new setJob function, me.setJob, with a new value. We'll say senior developer. And if we print the value of getJob again, console.log me.getJob, we'll see that it prints the updated value. Again, I really want to stress that these functions are the only access we have to this job variable, thanks to the magic of closure. If we try to access the job variable as a property of our person object, we get undefined, like this. This will be undefined. As an exercise, why don't you try writing the setAge setter for our person object? We've spent quite a bit of time in previous videos talking about first-class functions in JavaScript. We've seen how JavaScript treats functions in much the same way as strings, numbers, objects, and arrays, and how this allows us to do things like pass functions as arguments to other functions and return functions from other functions. Now, there's a term for functions that either take other functions as arguments or return functions. We call them higher-order functions, and using them in our code can provide amazing flexibility and reusability. To demonstrate this fact, we're going to look at some examples of higher-order functions and what they can do. The first thing we're going to use higher-order functions to solve is the problem of checking arguments in JavaScript. It happens quite often in programming that we want to make sure our arguments meet certain criteria. We might want to make sure that our arguments are the correct types, for example, or we might want to make sure that a number we pass in is positive, or that two arrays that we pass in have the same number of elements. There are many different situations like this that we might run into in our programs. Now, normally when we want to perform these kind of checks, they make their way into the body of our function. Let's take a simple example of writing a division function. A function that takes two arguments and divides the first argument by the other, like this. Const divide equals x, y, return x divided by y. Obviously, we'd like to prevent the second argument from being 0, so we add that condition to the function body like this. First, we have to add brackets and the return statement. And we add an if statement that looks like this. If y is equal to 0, then we want to log an error to the console. It'll say something like error dividing by 0. And then it will do something like return null. And this will prevent our function from returning not a number when the second argument is 0. Now, this works, and this pattern of argument checking is quite common in many code bases, but now we're cluttering up our divide function with argument checking logic. The single responsibility principle, a very important principle to follow when writing clean code, states that each piece of code should have only one responsibility. In other words, if describing what a given piece of code does requires you to name 2 or more things, it's a sign that you should refactor. In our case, our divide function is not only returning the quotient of 2 numbers, but it's also worrying about checking that the arguments fit a specific criteria. Let's see how we can improve this code using higher order functions. Our basic plan of attack here is to have our divide function only worry about returning the result of division. So instead of including the argument checking logic inside the divide function, what we're going to do is create another function. We're going to name this function with the rather lengthy name of second argument isn't 0. And what this function will do is take a function as an argument, we'll call it func, and this func argument will represent the function that we want to call if a given criteria is met. So we'll be returning a function, and for the arguments here, we're going to use the ES6 spread operator to get all the arguments we pass in as an array. Then, inside this function that we're returning, we're going to perform the argument checking. In our case, it's going to be almost exactly the same as this if statement we defined inside divide, except instead of checking y, we're going to make sure the second argument isn't 0. And the second argument, of course, has the index of 1. And then, if we get past this if statement, what we're going to do is return our original function argument that we passed in, called with all the arguments that we passed in. And remember here that we also have to use the spread operator. And that's what our second argument isn't 0 function is going to look like. Now let's see how to use it. First, let's delete the checking logic from divide so that all it's doing is returning the quotient of the 2 arguments we pass in. So using this function is quite simple. All we have to do is define a new function. We'll call it divideSafe, so const divideSafe, equals second argument isn't 0, and we're going to pass the divide function as an argument. We can now call our divideSafe function in the exact same way that we called our divide function, like this. Console log divideSafe, and we'll pass 7 and 0. And if we run our code by typing npx babel-node cho2/start/examples.js and run our code, we see that it correctly logs the error and returns null, just as we wanted it to. And the nice part here is that both our divide function and our second argument isn't 0 function only have one responsibility. Divide's function is to find the quotient of the 2 arguments, and our second argument isn't 0 function, its job is just to check the second argument and make sure it isn't 0. And of course, if we try and call our divideSafe function with arguments that will pass the check and run our code again, it will give us the correct result, which is exactly what we want. One of the nice things about learning functional programming with JavaScript is that many of the concepts we've learned have a great deal of native support in the language itself. In general, JavaScript, and in particular ES6, makes it much easier to apply many of the core functional programming concepts than if we were working in languages such as Java or C++. One of the areas where this fact is especially true is in working with objects and arrays. JavaScript provides a host of built-in functions and functionality that makes working with these constructs in a functional way incredibly easy. Built-in functions such as map, filter, reduce, and sort make the formerly complicated task of transforming array data almost trivial. As you're studying these functions and learning about what they can do, you may start to wonder how these functions work under the hood. The sort function, for example. What sorting algorithm does it actually use to sort our array? Quicksort, bubble sort, merge sort? Well, the beautiful thing is, it doesn't matter. Functional programming, as we saw in previous videos, is meant to free us from having to worry about how things are done, and instead just focus on what things are. If you want an array of names sorted alphabetically, you can just say so. You don't have to worry about all the mechanics behind what makes these functions work. Leave that to the browsers and node servers. In fact, many browsers actually implement these functions differently depending on what works better for them. Anyway, that's just something to keep in mind as you learn about JavaScript's many built-in functions to help you manipulate data. If you find yourself worrying about how something works behind the scenes, well, it might be a fun mental exercise, but at the end of the day you can just sit back and relax because as a functional programmer, that's not your job. Over the course of the next few videos, we're going to examine ES6's built-in support for functional programming and how we can use it to our advantage. ES6 offers many syntax improvements over its predecessor, CommonJS. In addition to arrow function syntax, which we covered in a previous video, and import-export statements, ES6 provides us with a new syntax that's really helpful for dealing with JavaScript objects and arrays, something that we do a lot of when doing functional programming in JavaScript, since these are the main ways that our data is represented in code. So this new syntax is called spread operator syntax. To see what the spread operator syntax looks like and how it works, let's imagine that we have two objects. The first object represents a person. We have their name, their age, and their hair and eye color. And the second object represents career data that we might have about the person, their job title and the company they work for. What if we wanted to combine these two objects into one object that had all the same properties and values as these two objects? Well, that's exactly what the spread operator helps us do. Instead of having to loop through each of the properties of the career data and set those properties on the person's object, which would involve a great deal of mutation, we can simply combine the two like this. And this is what the spread operator syntax looks like. So let's define a new object. We'll call it person with career data. And we'll have the brackets. And this is where we use the spread operator. We simply put 3 dots, and then our person object, comma, and then 3 dots, and then our career data object. And what this does is it creates a new object with all the properties of both person and career. If we print this new object, console.log, person with career data, and then run our code, npx babel-node, ch03, 03, 02, /start/examples.js, and run it, we see that this object has the properties and values from both of our other objects. In other words, the spread operator allows us to sort of spread the properties of one object inside another, as we've done in this example. Of course, we don't necessarily need to combine all the properties of both these objects. For a particular program we're writing, it might be enough just to have the person's name along with their career data, which would look like this: name, person.name. And if we run it again, we see that our new object now only has the name, title, and company properties. Note that when using the spread operator, if the objects that we're spreading have property names in common, for example, if both the person data and career data have a name property, whichever one comes last will overwrite the ones that come before it. So for example, if we change this back to just be the spread operator, person, and we give the career data a different name than the person data, and then we run our program again, we'll see that the name from the career data overwrites the name property from the person data. And this can be quite useful when we have a person object and want to update some of the properties. What we can do is create an updates object, const updates, which contains the fields that we want to update as well as their new values. For example, if we want to change our person's name, James Smith, we can then create an updated person, const updated person, and set it equal to the spread operator person, and then the spread operator updates. And if we print this, updated person, and run our code, we see that it now contains the updated name property instead of the original name property. So far we've seen that the spread operator can be used for objects, but it can also be used with arrays as well. If we have an array, for example, and we want to add some elements to it, let's create our array. We'll call it numbers, const numbers, and it'll just be 1, 2, 3, 4, 5. Instead of using the push method, which mutates the array it's called on, we can use the spread operator to combine the old array with the new elements we want to add to it. And that looks like this. We'll say const new numbers, array, and then 3 dots, and then numbers, and whatever new element we want to add. If we then print this new numbers array and run our code, we see that the new array now contains all of the numbers from our original array, as well as whatever numbers we added after the spread syntax. Of course, we can also add new elements to the beginning of the array just as easily by placing the spread operator after the elements we want to add. For example, if we wanted to put 0 before our array. And if we run our code again, we see that our new array now contains 0 at the beginning, and then all the numbers from our original array, and then 6 at the end. The first of JavaScript's built-in array functions we're going to be talking about is called map. Quite often it happens that we have an array of data, and we want to convert each of the individual elements in the array to some other form. For example, we might have an array of numbers, and we might want to double all the numbers in the array. Or we might want to convert an array of inch measurements to an array of centimeter measurements. Or we might have an array of person objects with name, age, and job attributes, and maybe a lot more data as well, and we want to convert this data into an array that contains only the people's names. The typical way of doing this, and the way that many of us first learned how to do it, was to use a for loop and an index variable to loop through all the elements in the array and push modified elements onto a new array. Or worse, we just modify the elements in place, which destroys the original data. However, as many of us know, this way can very easily lead to bugs, especially as the body of the for loop gets bigger and more complex. Fortunately for us, JavaScript provides a much easier, cleaner, and more functional way of doing this using its built-in map function that we can call on any array. The way we use map is by calling it on an array and passing it some function we want to apply to each element in the array. Map then returns another array that contains the return values of the function for each element in our original array. So in other words, it takes each element and maps it to the return value of the function we give it. If this function does something like square a number, for example, map will return a new array where each of the numbers has been squared. Now, before we continue, there's one important thing to note about the built-in array functions. Some functions like map don't actually change the original array we're calling the functions on. They just return a modified copy. So just calling map on an array, for example, without defining another constant to hold the result, essentially does nothing. But keep in mind also that this is not the case for many other built-in array functions in JavaScript. The reverse function, for example, if we call numbers.reverse, actually does modify the original array that you call it on. So for example, if we log numbers now, console.log numbers, and run our program, npx babel-node ch03/03_03/start/examples.js, and run it, we see that reverse has actually mutated our original array, which obviously we don't want. And if you're using ESLint to warn you of unwanted mutation in your code, as we talked about in a previous video, you should be able to guard yourself against this fairly easily. And if you're not using ESLint, well, be careful. So earlier in the video, I mentioned a few examples of how map might be used in our programs. Let's go through an example to solidify our understanding of what map looks like in code. Again, the typical procedural way of doing this is something like this. We start off with our numbers array. We create another array. We'll call it doubled numbers, and make that an empty array. And then we'll write a for loop that cycles through each element in the array, does something to it, and pushes it onto the new array, like this. For let I equals 0, I is less than numbers.length, I++, and then doubled numbers.push, the new element, which will be numbers I times 2. Now this works, and it's not necessarily a bad way of doing it, but the main problem here is readability and conceptual purity. If we want to double all the numbers in an array, we shouldn't be forced to worry about indexing and array lengths and off-by-one errors. We should be able to program in a way that allows us to simply specify what it is we want, instead of how to compute the result. And that's exactly what functional programming allows us to do. Let's look at how we can do the same thing in a functional way. We're going to rewrite this functionality using the map function. First, we're going to write a function called double. And this function is simply going to take one argument and double it. And all we have to do now is define a new constant, const, doubled numbers, and call the map function on our numbers array, numbers.map, and finally we're going to pass our new double function to map, because we want to double each element in our array. Let's log this to the console and run our code. Console.log, doubled numbers. And we see that it works beautifully, with the added benefit that it's now much easier to read and maintain. We don't have to worry about indexing or exceeding the length of our array, since map takes care of all that for us. All we have to think about now is how we want to transform each element in our array and express that in a function like we did with double. The next important built-in array function is called filter. Filter is used when you want to find all of the elements in an array that fit some kind of criteria. For example, if we have an array of numbers and we want to get all the numbers from it that are even, or if we have an array of employee data and want to find the employees from this array that make more than a certain amount per year, these are things that filter can help us with. The syntax of filter is similar to map. We can call it on any array and then we pass in a function. The main difference between filter and map is the type of function that we pass into it. In map, we pass in a function that returns a value for each element in the array. And the return value of this function represents what the element becomes in our new array. On the other hand, for filter, we pass it a function that returns either true or false for each element. If the function that we pass returns true for a given element, then that element is included in the final array. Otherwise, it's left out. Let's look at a few examples of what using filter looks like. For our first example, let's say again that we have a simple array of numbers and we want only the even numbers from the array. Again, the typical procedural way to do this would be like this. We define a variable called even numbers, which is an empty array, and then we create a for loop to loop through all our elements, and if an if statement is true for a certain element, we push that element onto our array, like this. First our for loop, for, let I equal 0, I is less than numbers, dot length, I++. And since we want to know if our numbers are even, our if statement is going to look like this. If numbers I modulus 2 is equal to 0. This is just a way of testing if a number is even. And if it is even, we want to push this number onto our even numbers array like this. Even numbers dot push numbers I. And again, this big for loop is pretty complicated for such a simple task. Let's see how to simplify it using filter. So first of all, we want to create a function. We'll call it isEven. And take this condition from the if statement. And then instead of numbers I, we just want to say x for the argument we pass in. Now instead of this big for loop, we can simply say const even numbers equals numbers dot filter is even. And if we print our even numbers array to the console, console.log even numbers, and run our code, npx babel node ch03 03 underscore 04 slash start slash examples.js, we see that it simply returns the even numbers from our array. And note here that it's not necessary for us to define isEven as a separate function before we pass it to filter. We could just as easily write it as an anonymous function inside the parentheses of filter, and that would look like this. We say x, arrow, and then the condition, x modulus 2 is equal to 0. Again, this is just checking if a number is even. And if we run our code again, we see that it works just the same. What if we have an array of words, like this, const words, hello, goodbye, the, and some other word like Antarctica. And let's say we want to find all the words from this array that are longer than 5 letters. Now, I'm not going to show you the for loop way of doing this, but you're free to write it out for yourself if you find that it helps you think about it more clearly. So first, what we'll do is define a function called isLongerThan5. Const isLongerThan5. And the argument, we'll call it word. And we simply want to return if the word dot length is greater than 5. And then we can simply say const longWords equals words dot filter is longer than 5. And let's delete this console.log statement so that it doesn't clutter up our console. And then if we log this longWords constant, console.log longWords, and run our code, we see that we get the 2 words from our words array that are longer than 5 letters. Now, those of you who watched the previous video about returning functions may have noticed that our isLongerThan5 function is strangely specific. Why 5? Why not 4 or 6 or 10? It's conceivable that in a larger program, there might be many places where we want to do this kind of filtering with different lengths. So let's write ourselves a higher order function that we can use to do this with minimal code. What we're going to do here is write a function. We'll call it createLengthTest. Const createLengthTest. And this function is going to take an argument that specifies the length that we want the function we return to test for. For example, if we want to create a function that tests if a string is longer than 4, or longer than 5, or longer than 10, etc. We'll call that argument minLength. And finally, we're going to return a function that looks just like our original isLongerThan5 function. We'll copy and paste that. Except, instead of testing if the string length is greater than a specific number, 5, we're going to test if the string length is greater than the minLength argument. Like this. And we'll add some spacing in here for readability. And now what we can do is, instead of defining our isLongerThan5 function like this, we can simply say that isLongerThan5 is equal to createLengthTest 5. And we can also simply cut out this middle step here and simply say words.filter createLengthTest 5. And if we do console.log longWords and run our program again, we see that it still behaves in exactly the same way as before. And this here is a very nice functional piece of code. Next, we're going to look at 2 built-in array functions that are pretty similar. These functions are called every and sum. We saw in a previous video how to use JavaScript's filter function to find the elements in an array for which a given condition is true, finding all the even numbers in an array of numbers, for example. JavaScript's built-in every and sum functions are similar to this in that we pass them a function that returns either true or false for each element. But the difference is that instead of returning an array, every and sum return a single Boolean, true or false. Every returns true if and only if a given condition is true for every single element in our array. Otherwise, it returns false. So for example, if we have an array of all odd numbers, and we call every with a function that checks if a number is odd, it will return true. But if there's a single even number in our array, it will return false. And of course, if the array contains all even numbers, it will return false as well. Now sum, on the other hand, returns true if the condition is true for any of the elements in our array. In other words, it returns false if and only if the condition is false for every element in our array. So taking the same example from before, if we have an array of all odd numbers and we call sum with a function that checks if a number is odd, it will return true. And if we have a single even number in our array, it will still return true, all the way down to if there's only one odd number in the array, where it will still return true. The only time it will return false is if we have an array of all even numbers. So then, comparing the output of every and sum, we see that their return values will be exactly the same if we call them on an array where the condition is either true for all the elements or false for all the elements. Where their outputs disagree is when the condition is true for some intermediate number of elements. This is where sum returns true and every returns false. It's worth noting that while there's no built-in none function in JavaScript to explicitly test if a condition isn't true for any elements in the array, we can easily get this same functionality using the not operator along with the sum function. This will return true only if a function is false for every element. Let's look at a quick example of how we might use these functions. Imagine that we're writing a payroll program and we have an array of employee data with name and salary information, and we want to find out if any of our employees makes more than $1 million a year. With sum, this is pretty trivial. We create a function called makes more than $1 million, const makes more than 1 million, that takes an employee as an argument, and returns whether or not that employee's salary attribute is greater than 1 million. Employee.salary is greater than 1 million. And let's put a space in here for readability. Then all we have to do is define a new constant. We'll call it result. And then do employees, our array of employee data, dot sum, and then we'll pass our makes more than 1 million function. And then we'll log our result, console.log result. If we run our function now, using npx babel node ch03/03_05/start/examples.js, we see that our result is true because one of our employees does make more than 1 million right here. Now, as an example of how every might be used, let's imagine that we're programming an online form for a website, and we want to check if the user has filled out all the fields before letting them continue. Let's imagine that we have our form values in an array of strings like this. Const form values, and then some strings that a user might enter into a form. For example, their first name, their last name, their state of residence, and then maybe they left one of the fields blank. So all we have to do to make sure that the user has filled out all the forms is create a function. We'll call it isNotEmpty, const isNotEmpty, and we'll simply return whether or not the string we pass it is empty. In this case, we can just use the double exclamation mark notation to convert our strings into booleans. And this works because in JavaScript, an empty string is a falsy value. Now all we have to do is define a new constant. We'll call it allFieldsFilled, const allFieldsFilled, and that will be equal to formValues.every, and we'll pass our isNotEmpty function to every. And finally, we'll log our result, console.log allFieldsFilled, and if we run our program again, we see that it returns false because we left one of these fields unfilled. If we fill that in, let's say it's your job title, and run our program again, we see that it now returns true because all the fields are filled. Notice again how readable it is to use these built-in functions. In this case, the right-hand side reads almost like a function. We want to check that every form value isn't empty. Again, this is just one of the benefits that functional programming gives us. The next built-in array method we're going to be looking at is called slice. Unlike the last few built-in methods we've seen, slice is not a higher-order function. It doesn't take a function as an argument like map or filter, but it does have some important uses when working with arrays in JavaScript. I mentioned earlier in the course that there are some array functions that mutate the arrays you call them on. Sort, which we'll look at in a later video, is one of those functions. And we also have push and pop, which add and remove elements from the array respectively, but also mutate the array. So as I've mentioned, these functions don't just return a copy of the original array, they actually mutate the original array. And this isn't always obvious. It's for this reason that I strongly recommend that you use ESLint, which I showed you how to set up in a previous video, to catch unintended mutations for you. So what does this mean for us? JavaScript provides these very useful built-in functions for us, but because functional programming prohibits mutation, and these functions mutate the arrays we call them on, we can't use them directly. So are we content to just not use these helpful functions? Of course not. As it happens, there's a very simple workaround to turn mutating functions into non-mutating functions. And the key to this workaround is another built-in function called slice. So let's take a look at slice. First of all, what does slice do exactly? Well, normally slice is used to get a section of the elements from an array. For example, if we have an array of numbers 0 to 10, we can get a subset of these numbers by calling slice. So numbers.slice. And the first argument tells slice which index of the array to start on. For example, 3. And the second argument tells slice which index to stop before. For example, 8, which means that the last element in our array will be the number 7, in this example. Now let's just log this to see what the result is. Console.log. And then we'll run our code using Babel Node. And here we see that we have a subset of our original array, starting at the index 3 and ending just before index 8. Now, fortunately for us, slice does not mutate the array it's called on. It returns a copy. So what if we used slice to simply create a copy of the array for us, and then called sort or one of those other mutating methods on that copy? All we have to do is take a slice which starts at the beginning of the array, at index 0, and includes the whole array. Well, as it happens, the default arguments for slice, if we simply call slice without any arguments, do exactly that. So if we run our code again, we see that we simply have a copy of the original array. This is really helpful to use with built-in array functions that mutate the array by default. All we have to do to stop JavaScript from mutating an array with these functions is to call slice with no arguments, and then call the mutating function after that. For example, reverse. And then if we run our code again, we see that we have a reversed copy of the array. In order to see that it's really not mutating our original array, let's log the original array as well. If we run our code again, and we see that our original array remained intact. So slice is very useful for this kind of situation. You'll see it more in coming videos. Now that we've seen how to use slice to prevent mutation, let's take a look at the function sort. As you may have guessed by the name, this function is used when we want to change the order of elements in an array. This would be very useful, for example, if we had an array of names and wanted to sort it in alphabetical order, or if we had an array of employees and wanted to sort them by the number of years they've been with the company, for example. Before we look at how to use sort, it's very important to remember that sort is a mutating function, which means that it actually modifies the original version of the array that it's called on. In a previous video, we saw how JavaScript's built-in slice function could be used to make a copy of an array, which would then allow us to use mutating functions such as sort without modifying the original array. And that's exactly what we're going to do with sort. So whenever we use sort, instead of simply calling it using array.sort, we're going to call it using array.slice.sort. Keep this in mind for all the examples we see using sort. So then, how do we use sort? Sort, like map, filter, every, and sum, takes a function as an argument. However, unlike the other functions, the function we pass to sort, called a comparator function, has 2 arguments instead of 1. These 2 arguments are a little more abstract and stand for any 2 elements in our array that could be compared. The return value of this function, for any 2 elements, determines the order in which these elements will appear in relation to each other in the final array. For example, if our comparator function returns a value less than 0, then the first argument will come before the second argument in the final array. If the comparator function returns a value greater than 0, then the first argument will come after the second argument in the final array. And finally, if the return value is equal to 0, then that signifies to sort that the numbers are the same and it will leave them in the same relative order that it finds them. This might sound a little complicated at first, so let's see what this will look like in a very simple example. Let's say that we have an array of numbers from 1 to 10 all mixed up like we have here. In order to get a sorted copy of this array, The first thing we'll do is define our comparator function, which will pass into sort to tell it what order we want our numbers in. Let's say that we want to sort our numbers in ascending order from 1 to 10. So we'll create a function and call it ascending. Const ascending. And this function will have two arguments. We'll call them a and b. Now, using the logic we discussed a minute ago, if our first argument a is smaller than our second argument b, we'll want it to come before b in our final array. So we'll want to return a value less than 0. We'll use -1. That'll look like this. If a is less than b, return -1. Otherwise, if a is larger than b, we'll want it to come after b in our final array, so we'll want to return a value greater than 0. We'll use 1. If a is greater than b, return 1. And then the only other case is if a and b are equal, so if neither of these other cases are true, we'll just return 0. Now that we have our comparator function, all we have to do is call sort on a copy of our array. Remember that we have to call slice first to create a copy, and that'll look like this. Const sorted numbers equals mixed up numbers dot slice dot sort, and then we'll pass our ascending function, ascending. Now if we print this to the console, console.log sorted numbers, and run our code, we see that we get the desired result. So far we've sorted our numbers in ascending order. What if we wanted to sort them in descending order from biggest to smallest? Well, to do this, all we have to do is make two small changes. We just have to change the less than and greater than conditions around. Let's copy our ascending function and rename this function descending. And then, as I said, all we have to do is switch the greater than and less than signs. Now if we pass our descending function to sort, and run our code again, we see that again it works perfectly. Note that these ascending and descending functions will work equally well if we're sorting arrays of strings. For example, JavaScript would return true for this statement here. Alabama is less than banana, for example. And again, as I mentioned before, the exact implementation behind the scenes of the sort function isn't important for us. And many browsers actually implement it differently depending on the array and several other factors. If you're curious about it, feel free to look it up. The final built-in array function that we're going to discuss is called reduce. The purpose of this function might not be quite as apparent as map, filter, or sort, but reduce is definitely just as useful as, if not more useful than the other array functions. What reduce allows us to do is take an array of data and reduce it down to a single value. So for example, we could take an array of numbers and reduce it down to a sum or an average. Essentially, what reduce does is starts with an initial value, say 0, and for each element in the array, it modifies this initial value in some way until after we've processed all our elements, we end up with the result. In the case of finding the sum of an array of numbers, for example, we'd add each element to the initial value over and over again until we find our final result. And if we were trying to find the product of an array of numbers, we'd multiply each element by the initial value and so on. So what's the syntax of reduce? Reduce, like most of our other built-in array functions, takes a function as an argument. The form of this function, however, is a little different from what we've seen with map and filter. This function, in its simplest form, takes two arguments. The first argument represents the current value that we've built up on top of the initial value. We call this argument the accumulator, and by convention, we just use the abbreviation ACC in the function's arguments. The second argument represents the current element of the array that we're looking at, much like in the map or filter functions. And the purpose of this function that we pass to reduce is to tell reduce how to combine the current value of the accumulator variable, what we've got so far, with the current element that we're looking at. When we want to calculate the sum of an array of numbers, for example, our function will simply return the accumulator argument plus the current element. There's one last thing we have to remember about the reduce function. In addition to the function that we pass it as an argument, we have to remember to provide it with another argument, the starting value. This is the value that reduce will start with when looking at the elements in our array. In other words, when the function we pass to reduce is called for the very first time, our accumulator argument will be equal to this starting value, and the second argument will be equal to the first element in our array. Since people often find reduce the hardest array function to grasp conceptually, let's take a look at what's happening exactly when we call reduce on an array. We're going to use the simple example of finding the sum of an array of numbers. So first, let's say const sum equals numbers.reduce, and when we're using reduce to find the sum, we'll want the starting value to be 0. Now let's define our function that will combine our numbers to get the sum. As I mentioned before, we usually call the first element ac. And for the second element, we're just going to use x. Now what we're going to do inside this function is log out ac and x so that we can better see exactly what's happening when we call reduce. So let's say console.log, and then we'll use backticks instead of single quotes, and then we'll log out the value of our accumulator argument. Ac is, and then we'll say the value of ac. And then we'll do the same thing for x. Console.log, backticks, x is, and then the value of x. And finally, what we actually want to return is simply the accumulator plus whatever element we're on, x. And if we run our code now, let's take a look at the output. So here we see that the first time our function is called, our accumulator argument will be 0, our starting value, and our second argument will be 5, the first number in our array. The next time our function is called, ac is the sum of our previous two numbers, and x is the second number in our array, 7. And after that, ac is the sum of our previous two numbers again, and x is the third element in our array. And then the fourth time it's called, ac is the sum of our previous two numbers, 12 plus 2, and x is the fourth number in our array, 40. And so on and so forth until we get our final result. And we can see our final result by logging sum afterward. So we'll say console.log sum, and then run our code again. And we see that our final sum is 114. In other words, 103 plus 11, which is the last number in our array. Now, note that if we wanted to use reduce to calculate the product of all the numbers in our array, the starting value we'd have to provide wouldn't be 0, it would be 1. If we change the return value here to find the product of all our numbers and keep 0 the same, we'll change this variable name to product as well. And then run our code. We see that the final result we get is 0 because our starting value is 0 and our first number is 5. And then the next time the function is called, the accumulator value is 5 times 0, which is 0. And then the next time it's called, it's 7 times 0, which is 0. And then the next time it's called, it's 2 times 0, which is also 0, and so on. So if we're finding the product, we want to make sure that our starting value is 1. If we run our code again, we see that we get a very large number, but it's working correctly. The first time our function is called, the accumulator variable is 1, our starting value. And then the next time it's called, it's 5 times 1, which is 5. And so on and so forth. And this is just something to keep in mind when using reduce. The starting value is very important and can be the difference between your reduce function working and not working. So far we've seen several of JavaScript's numerous built-in array functions, their syntax, and some examples of how they might be used in a codebase. These functions are certainly very powerful on their own, and each contributes a great deal towards simplifying and increasing readability in our code. The really exciting part, however, is that these functions can all be combined to give us an incredible amount of functionality. In this video, we're going to walk through an example of how we can do this. The example we're going to look at is this. Let's say we have an array of employee data, each with name, age, job title, and salary attributes. Now, there's all sorts of interesting information that can be deduced from a data set like this, and we're going to examine a few ways that we can discover this information using the built-in array functions we've learned. What we're going to do is calculate how the average salary of the developers in our data set compares to the average salary of the other people in our data set. First, let's collapse this so that it's more readable. The first array function we're going to use for this calculation is filter. We want to use filter to separate the developers from the non-developers. And the way we do this is by defining a new constant. We'll call it developers, const developers. And we're going to call filter on our employees array. Employees.filter. Since we want filter to give us an array containing only the employees from our array whose profession is developer, we'll simply define an anonymous function here, which returns whether or not an employee's profession is equal to developer. And that'll look like this. The argument we use will be called employee, and we simply want to return whether employee.jobTitle is equal to developer. Let's print out this array to make sure we're on the right track so far. Console.log developers. Now if we run our program, we see that we have an array that contains all the developers from our original employees array. And this is exactly what we want, so let's move on. The next thing we're going to do is transform our array of developer objects into an array of only their salary attributes. And to do this, we'll use map. So what we'll do again is define a new constant. We'll call it developer salaries, and we'll call map on our developers array. For the function we pass to map, we just want it to take each developer object and map it to their salary attribute. And that'll look like this. We'll call the argument of our function developer, and we'll simply return developer.salary. And the final thing we have to do is calculate the average of the values in our developer salaries array. The first step of this is to calculate the sum of the array. We went over this in a previous video, so I won't spend too much time discussing it. But in order to find the sum of all the values in this array, all we need to do is define a new constant. We'll call it total developer salaries. And then call reduce on our developer salaries array. Developer salaries.reduce. And remember that the function that we pass to reduce is going to have two arguments, our accumulator argument, and x, which stands for each of the elements in our array. And finally, we're going to return our accumulator plus x. And let's not forget to set the starting value to 0. And the only thing left to do is divide our total developer salaries, the sum of all the developer salaries, by the total number of salaries. So we'll define a constant called average developer salary, and that'll be equal to total developer salaries divided by the length of developer salaries. Developer salaries.length. And this should give us our answer. Let's log it to the console. Console.log average developer salary, and run our code. And the result we get is the average salary of all the developers in our original employees array. Now that we've found the average salary of our developers, let's find the average salary of our non-developers. So the first thing we're going to do is define a constant called non-developers and call filter on employees. And we want to get an array that contains the employees whose job title is not developer. And that'll look like this. We have our employee argument, and we want to return whether employee.jobTitle is not equal to developer. And the next step, as we did above, is to map this array of non-developers to simply an array of their salaries. So we'll define a new constant called non-developer salaries, and we'll set it equal to non-developers.map, and for the argument we'll just say non-dev, and we want to map the non-developer to their salary attribute. So non-dev.salary. After that, we want to find the sum of our non-developer salaries. So we'll call that total non-developer salaries. And that'll be equal to non-developer salaries dot reduce, and this will be the same as we had above. Accumulator x, and we want to return accumulator plus x. And don't forget the starting value. And then, just as we did above, in order to get our average non-developer salary, we simply divide the total non-developer salaries by the length of the non-developer salaries array. Non-developer salaries dot length. And that should give us our result. Let's log it to the console. Console.log average non-developer salary. And if we run our code, we see that we get the two results. So we've seen in this video that there's quite a bit we can do by combining JavaScript's built-in array functions. Compare how simple and straightforward this was with doing the same task using for loops. I'll leave that as an exercise for you. Now that we've had a lot of practice with JavaScript's functional parts, such as built-in array functions, let's do a challenge. The challenge here, to make sure you really understand how the map function works, is to recreate the map function. Specifically, what we want to create is a function called map that takes two arguments. The first argument is an array, and the second argument is a function that should be applied to every element in the array. Your task is to recreate the map function in this way, obviously without using JavaScript's built-in map function. There are quite a few different solutions to this problem, but one of the easier solutions is to use a for loop, and one of the harder versions is to use only JavaScript's built-in reduce function. You'll want to write your code inside the body of this map function here. And if you've implemented it correctly, when you run your code, these lines here should print the correct answers to the console. This will probably take you about 10 minutes. Once you've completed it, check out the solution video where I show you how I solve this challenge. Okay, so let's take a look at two possible solutions to the challenge of recreating the map function in JavaScript. We'll start with one of the easier possible solutions of using a for loop. Inside our function body, the first thing we want to do is define a new array so that we don't mutate the array that we pass into our function. That would go against functional programming's core tenet of immutability. So let's write let, since we'll be modifying this variable, a new array, and the initial value will just be an empty array. And what we want to do now is iterate through all the elements in our array using the old index method from procedural programming. So we'll write for let I for index equals 0. I is less than array.length and I++. And for each element in our array, we want to get the value of the result that we get when we call our function argument on the element. And that'll look like this. Const result equals func array index I. And then we want to push this result onto the new array that we defined. And that'll look like new array dot push result. And of course, we want to make sure we return our new array once all the elements have been pushed onto it. Let's test this by running our code. And we see that the results that get printed to the console are exactly the ones that we were looking for. So great, that works. Now let's move on to one of the harder possible solutions to this challenge, recreating map using only JavaScript's built-in reduce function. For the body of our function, the first and most obvious step is to call reduce on our array. Array.reduce. Let's start off by thinking about what we want our starting value to look like. In this case, since we're building up an array, we're going to want our starting value to just be an empty array. Now, the accumulator function that we pass to reduce will look like this. It'll have two arguments, the accumulator and the current element in the array. We'll call it x. And what do we want to return? Well, we want to return an array that contains all the elements that we've accumulated so far. We'll use the spread operator for that. ... accumulator. And to this array, we want to add the result that we get when we call our function argument on the current element, like this. Func x. And make sure you either remove the brackets from the function body or use the return keyword. Otherwise, your map function will always return undefined. And that's it. If we run our code, we see that again we get the correct results printed to the console. So you can see that both of the possible solutions work. And depending on your situation, either one of the solutions might be better for you. So far in this course, we've covered a wide range of functional topics. We've learned how to think about our programs in a more functional way by covering the three main concepts. We've learned to work with first-class functions and various applications of doing so. And finally, we looked at how we can work with arrays in a functional way. The things we've learned up until now are extremely useful, and knowing these concepts and applying them in your code base will quickly show you the positive impacts they provide. But before we wrap up this course, there are two more concepts I'd like to cover with you. These concepts are recursion and partial application. Keep in mind that these concepts are more advanced, so don't worry if they don't really click with you at first. Furthermore, what I'll be covering in this course with regards to these concepts is only the tip of the iceberg, and a whole course could probably be made about each of these concepts alone. That being said, these concepts do serve as a great jumping-off point to get into more complex functional programming. If you stick to it and gain a thorough understanding of these concepts, they can allow you to do some very cool and flexible things, as well as gain a better understanding of functional programming in general. The first advanced concept we're going to look at is called partial application. In simple terms, partial application is when we take a function that has some number of arguments, and we fix some of those arguments to a set value. This gives us a function with less arguments than we had before. This function with fixed arguments can then be called from anywhere else in code, and it will be as if we had called the original function with all of its arguments. Partial application is a very useful way to configure more general functions into more specific ones. In general, if there's a function that we use often in our code, where one or more of the arguments that we call it with is almost always the same, this is a good candidate for using partial application. So now that we know what partial application is, what does it look like in code? Well, let's imagine that we have a simple add function, const add, and it takes three arguments, we'll call them x, y, and z, and adds them together, x plus y plus z. What if we wanted to fix one of these arguments to a certain number so that we only had to pass in the other two arguments later on? Well, that would look like this. We'll create another function, we'll call it addPartial, and this function will take a single argument. We'll call that x. It will then return another function which takes the remaining two arguments, y and z. And finally, this function that we return will call our original add function with all three arguments. And we can then call our function like this. We'll say const add5 equals addPartial with 5. Now the 5 that we're passing to addPartial becomes x, which is the first argument that we end up passing to our add function inside addPartial. So basically we're fixing x in our add function to a specific value, 5. We can then call our add5 function like this. We'll say const sum equals add5, and then we pass in the remaining two arguments. We'll say 6 and 7. If we log the result, console.log sum, and run our code, we can see that we get the sum of the three numbers, just as if we had called add with all three numbers to begin with, like this. Add 5, 6, 7. If we run our code again, we see that we get the exact same result. So basically what we're doing with partial application then is instead of passing in all our arguments at the same time, we're simply passing them in at different times in different parts of the code. Now in this example we fixed the first argument and left the other two. In reality we can really divide up our arguments however we want. For example, we can partially apply the first two arguments and leave the last one for later, and that'll look like this. We'll simply take our y argument here and move it up here with x. Then the function that we return will only take the remaining z argument. And calling that will look like this. We'll say const add 5 and 6, and that'll be equal to addPartial with the x and y arguments as 5 and 6. And then we can say const sum equals add 5 and 6, and pass in the remaining z argument that we haven't passed in yet, 7. And if we run our code again, we see that again we get the exact same result. We can also go one level deeper and pass in each of our arguments one at a time. And what that'll look like is this. First we'll pass in our x argument, and we'll return a function that takes the y argument, and finally we'll return one last function that takes the z argument, and then calls add with x, y, and z. And calling this function will look like this. First we pass in our x argument. We'll call this add 5 equals add partial 5. And then we'll pass in our y argument. So we'll say const add 5 and 6 equals add 5. And we're passing in our y argument, 6. And this add 5 and 6 function that we have here is this function here that we return, which takes a single argument and then calls our original add function with all 3 arguments that we've passed in. So we can say const sum equals add 5 and 6, and we're passing in our z argument here. That'll be 7. And that should give us the result. If we run our code again, we see that we get the exact same thing. Now this sort of partial application where we pass in our arguments one at a time has a special name, and this is called currying. So when you hear talk of currying in the programming world, now you know what it means. Keep in mind also that we don't necessarily have to define all these intermediate functions. In the case of our add partial function here, we could simply call it like this, const sum equals add partial, and then pass in our functions this way. Now this might look a little funny, but it works exactly the same way. If we run our code, we see that once again we get the exact same result. The next advanced concept we're going to look at is called recursion. Recursion is a concept that you've probably heard of before, but maybe you've never seen it in action. What recursion is simply a case when a function calls itself. While doing this can very easily lead to an infinite loop if we're not careful, it can also be used to solve certain problems that aren't easy to solve using other methods. Let's take a look at a very simple example using recursion. We're going to create a function that behaves like a for loop without actually using a for loop. We'll call this function countdown. So const countdown. And what this function will do is start at whatever number we pass into it as an argument. We'll call that argument x. And it's going to use recursion to count down from that number to 0, printing the results along the way. So all we have to do is print the number, console.log, x, and then call our function with our argument -1. Count down, and we'll pass x minus 1. If we were to run our code now, it would recurse infinitely because we forgot one important thing. In recursion, we always have to tell our function when to stop. Without a stop condition, any recursive function will go on infinitely. Our stop condition in this case will be when the argument that the function receives is less than 0. So up at the top of our function, we want to say if x is less than 0, and then we simply want to return. This prevents the function from calling itself again at this point. Now if we call our function, countdown, and we'll pass in the number 10, and then we run our code, we see that it counts from 10 all the way down to 0 without using any kind of for loop. So what if we wanted to count up instead? Well, this is going to be very similar to counting down with a few small changes. First of all, instead of subtracting 1 from the number on each function call, we're going to add 1. Second of all, instead of checking to see if the current number is less than 0, we're going to check if the current number is greater than the number we want to count up to. And this means that we need to add another argument. So now x will be the number that we start on, and we'll define another argument called max that we want to count up to. Then, inside this if statement, we simply check if x is greater than max, and if it is, then we prevent our function from calling itself again. We also need to make sure to pass this max argument when our function calls itself. And finally, let's rename this function to countUp. And when we call this function initially, we have to define the number that we want it to start on, x, as well as the number we want it to count up to. We'll do 10 again. And if we run our code, we see that it prints the numbers from 0 to 10 counting up. And this is exactly what we wanted. We now have a function that counts up without any help from a for loop. Throughout the other videos in this course, we've consistently seen that the way we treat functions in functional programming is quite different from what we might be used to in, say, object-oriented programming. We've seen that they can be treated like other types, such as strings or numbers, and also that we can pass them as arguments into other functions or return them from other functions. Well, there's another aspect of functions in JavaScript that we're going to talk about today. In addition to the many other roles we've seen them play so far, the functions that we define in our code are also objects. So when we say that functions are objects, we mean that they have properties like objects do. They have a name property, for example, that returns whatever name we gave the function. So for instance, if we define a function called sayHello, that just prints hello to the console, we can say sayHello.name, and if we run our code, we see that that gives us the name that we initially gave the function. Now functions also have a length property which returns the number of arguments that a function expects. If we use our add function from previous videos that takes 3 arguments, like this, const add equals xyz, and returns the sum of xyz, the length property of add is going to be 3 since it expects 3 arguments. Functions also have properties which themselves are functions. For example, every function has a toString property which returns a string representation of the function's code. So if we say add.toString and print it, and then run our code again, we see that it prints a string representation of our function. There are 3 other function properties which are of interest to us from a functional standpoint. These functions are called call, apply, and bind. Let's start by looking at call. What call does is basically just calls our function. So we can say add.call, and the first argument of this call function allows us to change the value of the this keyword if we used it in our function. Now, in functional programming, we'll only use the this keyword inside functions very rarely, so we usually just end up passing null here for the first argument. And the rest of the arguments that we pass to call will be passed to our function and the result will be returned. So if we say 1, 2, and 3, and run our code, we see that call simply calls our add function with the arguments 1, 2, and 3. This is exactly the same result as if we had simply just called add and passed in our 1, 2, and 3. The next function we're going to look at is apply. Apply is almost exactly the same as call. The only difference is that instead of passing the arguments we want to call our function with in the usual way, we pass apply an array of values, which it passes to our function as arguments. So if we want to do this example here using apply, that would look like this. Add.apply, and the first argument that apply takes as well allows us to change the value of the this keyword if it's used in our function. Again, this will just be null. And then we can pass in our arguments as an array. We'll pass in 1, 2, and 3. And if we run our code, we see that we get the same result. Now, in reality, we'll rarely use either of these functions in our code. First of all, as I said before, in functional programming, we rarely have any desire to use the this keyword inside of our functions. This is something that's seen much more often in the world of object-oriented programming as a means to control internal state. But also, while prior to ES6, apply was the easiest way to call a function when we wanted to pass the arguments as an array, ES6 now provides us with a very neat syntax for doing this using the spread op. And that looks like this. If we define a constant called args, and set it equal to an array with 1, 2, and 3 in it. If we want to call add with this array, we can simply do it like this, using the spread operator and args. And if we run our code again, we get the same result. So even though the functions call and apply don't have a whole lot of practical use in everyday functional programming, in my experience, call and apply have a habit of showing up in job interviews for JavaScript-related jobs. So it's not a bad idea to at least know how they work. The last function we're going to look at, which does have some real practical application in functional programming, is a function called bind. Bind also lets us change the value of the this keyword when it's used inside our function. Again, this is usually null. But the useful part comes in the next arguments that we pass. In a previous video, we touched on partial application and how it allows us to fix the value of certain arguments in a function and return another function that we can use to pass the rest of the arguments to get the result. Normally, doing this requires somewhat complicated syntax, as we saw before, but bind allows us to do this in a much cleaner way. If we want to fix one of the arguments in our add function, we simply have to call bind and pass it the value we want to fix the first argument to. So if we wanted to fix the first argument to x, we could just pass 1 as the second argument to bind. This partially applies our function so that we can do stuff like this. Const add1 equals add.bind, null for the first argument, and we'll fix the first argument of our add function to 1, and then we can simply call add1 with the remaining two arguments. And if we run our code, again, we get the same result. And this can be very useful to use in our functional programming in many ways. To close out this course, we're going to do a few challenges that require you to use functional concepts to solve problems. And our first challenge is this. Let's say that an election has happened in our hometown, and we have an array of the votes, which are just strings with the person's name. Now, first of all, please note that none of these names is in any way meant as a reference to any candidate who's currently running in any election. So what we want to do is write a function that takes this array of election votes and produces an object like this, with the candidates' names and the number of votes that they had in the array. Now, this might not seem too hard, but there are a few catches. The first catch is that you're not allowed to hard code any of these names into your function. For all practical purposes, assume that you don't even know what names are in this election votes array. We want to write a function that in theory could work with any array like this. The second catch is that, since this is a functional programming course, you're not allowed to use any kind of mutation in this function. So when you think you've got a solution, feel free to go on to the next video where I'll show you how I solved it. So I'm going to show you how I solve this now. First of all, the tricky part here is that we want this function to be independent of the names that are actually in the array. As I mentioned before, we're not allowed to hard code any of these names into the function. So what I'm going to do for this function is use reduce. So we're going to say return votes.reduce. And remember that reduce takes two arguments, the accumulator, which will be the votes that we've tallied so far, and the current element, which will be the name of a certain candidate. And now before we write out our function body, we have to think about what we want the starting value to be for our reduce function. What do we want it to start out with? Well, since our expected output is an object, it would be a pretty good guess to say that we want our starting value to be an object. And in my case, it's exactly what I'm going to do. So now let's write the body of the function that we're passing to reduce. Again, since we want the final return value of this function to be an object, the thing that we're returning from this function here is also going to be an object. And since we're using arrow syntax here, we're going to have to remember to wrap it in parentheses, and then the brackets of our object. Now at any given point, this accumulator argument is going to be some earlier stage of our final result. So when our reduce function first starts out, the accumulator is going to be an empty object, and the name is going to be the first element in our array. And then when reduce gets to the second value of our array, the accumulator is going to be an object that looks like this, and our name argument is going to be the second value in our array. And so on and so forth until we obtain our final result. So what we want to do inside this object here is use the spread operator and spread our accumulator variable. This will put all the names and counts that we have so far into this object that we're returning. And then underneath that, we want to add another property to our object. Now this property is simply going to be whatever name that we're currently on in the array. And what we want to do, let's say that this is the object we have so far, and we get to this same name again, is we want to increment this number. So what we're going to do is say accumulator, and we want to get this property from our accumulator. So we'll say name, and then we're going to increment it by 1 like this. If we run our code now, we can see that the result that we get is not exactly what we want. Our object successfully contains all the right people's names, but the values for these names, where the count is supposed to be, is not a number. Now I'll tell you why this is, and it's because of this line here. The problem that we're running into is if this ACK variable, if our tally so far, doesn't contain a person's name, this here is going to return undefined. So we'll be doing undefined plus 1, which is not a number. And then it will simply propagate like that as we go on. So what we need to do is define what happens the first time we see a name. And the way we're going to do that is by checking if this accumulator argument already has a value for this name. And that'll look like this: accumulator, name, and then we'll use the ternary operator, so we'll just use a question mark. And so far we're saying that if this accumulator variable has this name already, we're going to return whatever the number is associated with that name, plus 1. So we just need to define what happens if that name doesn't exist. Well, since this means that this is the first time we've seen this name, we're going to want the starting value to just be 1, like that. And that should do it for our tally votes function. If we run our code again, we see that we get the right vote counts for everything. You can go back to the array and actually count them if you want, but just trust me that this is correct. And that's all there is to it. This is just how I solved it. You might have done something different. Keep in mind also that since the body of our function is only 1 line, we can remove these brackets here and delete the return keyword. And that's all there is to it. The next functional programming challenge we're going to tackle in this course is the problem of finding anagrams for a given word. Now, if you don't know what anagrams are, they're 2 or more words that have the exact same letters and number of letters. For example, Iceman, Cinema, and Anemic. Each of these has 1 A, 1 N, 1 E, 1 M, 1 I, and 1 C. So your challenge is to write the body of this function that takes a word as an argument and finds all the anagrams for that words in the second argument here. This second argument will be an array of all the words in our dictionary. Now before you start this challenge, note that we're importing something up top here. This is an NPM package that exports an array of all the words in the English language. So in other words, it's a really big array of strings. And before we can do anything, we have to install this package. So just open up a terminal inside your directory, and we're going to type npm install --save, and then an-array-of-english-words. And then hit enter. And once that installs, you're free to start working. And I've given you a little hint here. Since the word we're passing in is going to be in the form of a string instead of directly in the form of an array, we want to get just an array of the letters in the word. And the way we do that is by doing this, by calling word.split with an empty string. That's just a little hint to get you started off. Well, when you think you've figured it out, feel free to go on to the next video and I'll show you how I've solved this. And keep in mind that the functional rules are still in effect here. You're not allowed to use any kind of mutation, and you're also not allowed to use regex, which could theoretically be used to solve this as well. And that's all you need to know. You're free to get started whenever you want. So I'm going to show you how I solved this Find Anagrams challenge. The way that I thought about it is this. When we have 2 words that are anagrams, that means that they have the exact same count of the exact same letters, but in different orders. So if order doesn't matter, then it might make sense for us to express our words like this, as an object that contains each of the letters that the word contains, with a count of how many letters it has. So for the word cinema, for example, it would look like this. We have one C, one I, one N, one E, one M, and one A. We could then do the same with all of the other words and check to see if they have the same sort of signature, the same count of each of their letters. So for instance, if we formed this same kind of object with the other words, Iceman and Anemic, which are anagrams of cinema, we would get two objects where all of the properties would be equal. Now those of you who completed the last challenge might notice that this looks a little familiar. This is the exact same functionality that counted the number of occurrences of a given string in an array. So the first thing we're going to do is copy and paste our tallyVotes function that we wrote in the previous function. And in order to make this less specific, let's rename it to countOccurrences. And then we'll rename the argument to array, just ARR. And we'll change that here as well. And since we're no longer dealing with names, we'll say string, str, 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 and str. And now that we have this countOccurrences function that we can use to convert an array of letters into an object that contains the count of each of those letters, let's create another helper function. We'll call this hasSameLetterCount. And what this function is going to do is compare two words to see if they have the same number of the same letters. So we'll say word1 and word2 for the arguments. And inside this function body, we're going to define two new constants. We'll say const word1count equals countOccurrences word1. And then since countOccurrences expects an array of letters instead of just a string, we're going to say word1.split empty string, as I showed you down here. And then we're going to do the same thing for word2. We're going to say const word2count equals countOccurrences word2.split empty string. And then our return value is going to look like this. We're going to do return, and we want to do object.keys, which will give us all the letters in our word1 count. And we're going to do .every. And now for each letter in word1 count, we're going to check to see if the associated number in word1 count, which we get like this, is equal to that number in word2 count, like this. Now this is still missing something, and to see what it's missing, let's finish our findAnagrams function first. So we don't need this anymore, I just gave that to you as a hint. And what we're going to do in findAnagrams, we're going to say return all words, which is our dictionary, .filter, and then for each entry in our dictionary, we're going to check if it has the same letter count as our word argument here. And that'll look like this. We'll say hasSameLetterCount, word, and entry. Now let's save our code and run it to see what we have so far. And this is going to take a while because our words dictionary contains a lot of words. And once it finishes, we see that it prints out an array of things that definitely aren't anagrams for cinema. But if we look a little closer, we can see that these words contain all of the same letters as cinema in the same amounts. For example, they have one C, one I, one N, one E, one M, and one A. But they also have a lot of other letters as well. So to fix this so that it only finds true anagrams, we just have to add another condition to our hasSameLetterCount. And for this condition, we basically want to check that word1 count and word2 count have the same number of letters in them. And this means that word2 count doesn't have any letters in it that word1 count doesn't have, which is the problem that we were dealing with down here. So to write that condition, all we have to write is object.keys, word1 count, .length is equal to object.keys word toCount dot length. And then we want to add an and in between these to make sure they're both true. And now if we run our program again, we see that it correctly gives us all the anagrams. So the only thing that we want to fix now is we want to make it so that find anagrams isn't returning the original word. And it's doing that now because obviously the word that we pass in has the same number of letters as the word that we pass in. So in order to get rid of that, all we have to do is on the end of this statement in our find anagrams function, we're going to write dot, and we're going to say filter, and the anagrams that we return, we want to make sure that it's not equal to the word that we pass in. So we'll just say anagram does not equal word. And we'll put some spacing between there to make it more readable. And now if we run our code one last time, we see that it gives us our desired output, even though it's not in the same order, which isn't a big deal. And that's it. That's just how I solved it. You might have come up with a different way. Now let's move on to our final challenge. This challenge is a lot more open-ended than the previous two, and it involves generating error messages for form values, like we might see on any sign-up form on a website. So up top here we have an object representing our form values. So for example, we might have a first name input box, a last name input box, and zip code and state input boxes. And the value that we have for each of these properties is the current value that's in the corresponding text box. We then have a separate criteria object that contains the checks we want to perform on each of our input boxes. Now I mentioned that this challenge is pretty open-ended, so I haven't filled any of these in yet. But the requirements for each of these fields is up at the top. So for example, the first name and last name have to be at least 2 characters long, the zip code has to be exactly 5 characters long, and the state has to be exactly 2 characters long. So your task is to use these two objects, and then write a function that takes both the input values, as we have up here, and the criteria, as we have here, and generates an array of error messages. I've put an example down below. Now because this challenge is a lot more open-ended, the answer that I come up with is certainly not going to be the only one. But I will give you a hint at how I'll do it. Inside this input criteria object, for each of these properties, I'm going to create an array of functions that we use to check against the values up here in this object. So for example, our first name criteria might look something like this. It'll be a function that takes a value argument, and then either returns an empty string or an error message depending on that value. Of course, you don't have to do it that way. Any way you can come up with to do this is good. But just make sure that you follow the core tenets of functional programming. For example, you're not allowed to use any kind of mutation in here at all. Well, once you think you've figured it out, feel free to go on to the next video and see how I did it. So now I'm going to show you how I solved this challenge. I want to emphasize again that this is just one of the many ways that it could have been done. You might have done it differently, and that's probably just as good. So first, let's decide what our input criteria is going to look like. I decided that when I was solving this problem, each of these was going to contain a series of functions. To do an example now, we'll just do one function. But I decided that this function was going to take one argument, which is the current value of this field, up in our current input values object. And these functions were going to test something. So for example, for our first name, we want to test if the length of the value, value.length, is greater than or equal to 2. And then if this was true, I wanted to return just an empty string. And if it was false, I wanted to return an error message. So we can say first name must be at least 2 characters. And note that I use the ternary operator here, but you could have done this just as easily with an if statement. So this function here that tests if a string is at least 2 characters long, we're going to copy this and paste it on our last name criteria as well. And we're just going to change this here to say last name must be at least 2 characters. And then we're going to do something similar for the zip code and state. We're going to copy and paste this in here. The only difference here is that we want to make sure the length is exactly equal to 5, which is the length of standard zip codes in the United States. And for the state, we wanted to make sure that the length was equal to 2 for the state abbreviations. And then we want to change the strings here as well. So we want to say zip code must be exactly 5 characters long. And then we'll say state must be exactly 2 characters long. And let's save it. Now we have to figure out what the body of our getErrorMessages function should look like. Basically, we have to take our inputs and criteria and combine them in such a way that we get out an array of the error messages, as we have here. So the first thing we're going to do is say return. We're going to get the keys from our inputs object, which are going to be the names of the different fields, like first name, last name, zip code, and state. And we're going to do reduce here. And for the function that we pass to reduce, we're going to have our accumulator, and then each of the elements we're mapping is going to be called field name. So since we want our final value to be an array, it makes sense that our starting value would be an array as well. And then for the body of this function that we pass to reduce, we're going to return an array here as well. And what we want to do inside this array is say spread operator, accumulator, and then we're going to want to do the spread operator again, and we're going to want to get the corresponding array of tests that we run from our criteria object. And that's going to look like this. Criteria, field name. So a field name is first name, for example, right here. It'll give us this array, and we want to map over that array, and for each of these elements, we'll call them test. We want to call that test on the value of the field name of our inputs object, which will look like this. And let's make sure we're using the right variable names here. This is called inputs instead of input. And then if we save our code and run it, we see that we get all of our error messages correctly. Let's see what happens if we change some of these values in our current input values object. For example, if we had the correct input for first name. If we run our code again, we see that it no longer gives us the error message for the first name field, which is exactly what we'd expect. And if we put in the correct zip code and run it again, we can see that it no longer gives us an error for the zip code either. So there's just one last thing we want to do. Instead of having these empty strings in our array, we only want our array to contain strings that actually have an error message. And that's pretty simple to do. All we have to do is at the end of this array that we're returning, type filter, and we want to make sure that the message exists, which we can do just like this. Now if we run our code again, we see that it got rid of the empty strings. And this works because empty strings are falsy values. So when our filter gets to an empty string, it will see this as falsy and leave the element out. So that's as far as I'm going to go. But if you want to improve this answer even more, notice that these functions here are all very similar. And this means that we could probably use the concept of first-class functions to configure our functions for us, so that we don't have to redefine them like this each time. But I'll leave that up to you. So we've covered quite a bit of ground in this course. If you're wondering where to go from here, a great next step would be to take whatever programs you've already written in JavaScript and try converting them to make better use of functional concepts. There's also a book that I'd highly recommend for those of you looking for an extremely in-depth look at functional programming. This book is called Structure and Interpretation of Computer Programs, and it's available for free download on MIT's OpenCourseWare website. Despite its rather dry-sounding title, this book is a fantastic guide to thinking about programming in a very flexible way. And finally, if you want to learn more about either functional programming or JavaScript, our library is full of great courses on both subjects. If you have any interest in seeing how the concepts we've talked about here are expressed in Swift, Check out my course about learning functional programming in Swift. And finally, if you want to see how to use JavaScript ES6 to write a full-stack web application using React and Node.js, check out my course about creating and hosting a full-stack React site.